So the reason why we're doing the analytic solution is because it's basically a separate method to get the same results as we've done so far for the harmonic oscillator. Back in the analytic solution, we sort of saw, or not the analytic, I'm sorry. Back in the algebraic solution, we sort of took Griffiths' word for the ladder operators and just introduced them without any warning. So it isn't necessarily something that we can actually derive on our own without getting sort of Griffiths to trailblaze the way for us. In contrast to that, the analytic method is a lot less mathematically rigorous, and it sort of takes advantage of sort of behaviors of certain functions to basically sort of finesse out a solution without having to focus more on actually trying to solve this system. It's a little bit unintuitive in regards to sort of some of the steps that are taken. However, it does actually makes it realistically we would be able to come to this solution on our own without sort of being handheld to get to it is what I'm trying to say. So hopefully this sort of helps for those who sort of aren't comfortable with the algebraic solution. This could hopefully sort of help you by providing an alternate method for solving for the quantum harmonic oscillator that relies less on sort of just taking the a-hat operators for granted and more on sort of developing your own sort of intuition and trying to actually solve this on your own. So we start, as always, with the stationary state in X for the harmonic oscillator. And the first thing we're going to do is we're going to introduce a change of variables that's been being recommended all this time, which is that when we're working with sort of harmonic oscillator potentials, it's always easier to switch variables to Y, which equals x times the square root of m omega over h bar. So if we change variables here from x to y, there's a few things we have to do. First off, we have a d2 psi by dx squared, so we have to use sort of chain rule to convert this into a derivative in y. So we can write this as d psi by dx can be written to equal d psi by dy times dy by dx. And we know dy by dx, that's just, square root of m omega over h bar. So this equals d psi by dx times square root of m omega over h bar. So plugging this into our x x stationary state, we're going to get negative h bar squared over 2m. And then multiplied, since this is two derivatives, we have two factors of square root m omega over h bar, so we get multiplied by m omega over h bar. And then d2 psi by dy squared. And then we're adding 1/2 m omega squared. And then the x squared, because we have this relation, becomes y squared times h bar over m omega. And this is equal to E, which is unchanged, multiplied by psi. So there's a bit of simplification we can do here. First off, we have an m here and an m here, so those automatically cancel. We also have an h bar here and an h bar up top, so that cancels one of the powers, it becomes 1. Over here, we have an m here and an m here, and then we have an omega at the bottom and omega squared at the top, so the squared goes away and we have just 1. So let's see. What we really have is negative h bar omega over 2 times d2 psi by dy squared plus that same factor h bar omega over 2 times y squared. And my apologies, I just realized I left out the psi term here. And then this equals E times psi. So our new goal is now to solve for this new sort of significantly simpler, at least in terms of sort of these all of these original really messy constants at the front. We can sort of we've gotten rid of most of them, and we have something that's a little bit neater. If we actually want to solve this, then let's try to isolate the d2 psi by dy squared. So then we have d2 psi by dy squared and then with our negative h bar omega over 2 factor is equal to, and actually let's get rid of the negative for now so we can get the order right. So this is going to be equal to h bar omega over 2 times y squared subtracted by e and then multiplied by psi. And then if we get sort of this constant over to this side as well, then what we have left is d2 psi by dy squared being equal to, and then the h bar omegas over 2 cancel, and we're left with y squared minus 2e over h bar omega multiplied by psi. And we're actually going to sort of redefine this as a new constant. We're going to call it k. So d2 psi by dy squared is actually equal to y squared minus k times psi, and we're defining k as this constant that equals 2e over h bar omega. Okay, now we have sort of both of our new and improved sort of neater solution. The problem is we can't just go about actually solving this algebraically, because if we did that, then we go back to sort of the ladder operators and all of the horrible messy stuff and introducing sort of the ladder operators and all the stuff that we did in the algebraic solution. So we don't actually want to solve this exactly. Instead, we're going to see if we can sort of take some approximations and simplify this down to make this into something that's much easier to solve. Because the whole point of the analytic solution is to sort of guess and check solutions by looking at the behavior of functions. So instead of solving this directly and introducing ladder operators and everything, which we've already done before, we're going to start looking at some limiting case scenarios and seeing if we can get any sort of insight on that. So first thing that is interesting is that k itself is an actual constant. So what that means is that if we're dealing with psi at very large values of y, this y squared term is actually going to dominate. So what we mean by that is that psi, we're going to approach d2 psi of dy squared being roughly equal to y squared psi when y is large. So this is just a common sort of second order differential that we've encountered many times before. We can either rewrite this as a cosine and sine differential equation, or we can rewrite this as an exponential equation. For our purposes, because we already know ahead of time what the actual solution looks like, we know that there's an exponential term in our solution, so we might as well just guess the exponential solution for this second order differential. We could, of course, use the cosine and sines as well, but that's going to end up with some difficulties later down the line, so we're just going to not do that. If you were actually deriving this yourself, you would have to do both and sort of check both. But since we have the prior knowledge of what psi actually looks like from the analytic solution, we're just going to go ahead and assume that the solutions are exponentials, in which case the solution for this is going to give us that psi is roughly equal to some constant a times e to the negative y squared over 2, and then plus some constant times b multiplied by e to the positive y squared over 2. And once again, this is under our assumption that y is a large value. So instantly, one of the things that we can see is that e to the y squared over 2 blows up at positive and negative infinity for y. So this thing is not normalizable if it remains in our solution. So automatically we can conclude that b has to equal 0. So because of that, psi is actually just roughly equivalent to a times e to the negative y squared over 2. And this is only true, once again, when y is large. So we've sort of approximated this. This is true at large y, but it isn't necessarily true at small y. However, what we can do here is that we don't necessarily need this exponential to disappear, because what happens is that there's nothing stopping us from guessing and checking a solution at this point and saying that psi is actually equal to some arbitrary function, we'll call it h of y, multiplied by e to the negative y squared over 2. So what this does is, by guessing a solution for psi, we don't necessarily know that psi has this form, but it's a pretty good guess because this h of y can be just any arbitrary function. And what this is saying is that we're guessing that there's some h of y function at the front of this exponential, and at large y, this thing approaches a constant, and we go up to ae to the negative y squared over 2. But at smaller y, this h of y is going to be what actually dominates the behavior. So once again, we don't actually know if this is the correct form. However, the whole point of the analytic solution is to sort of guess and check based off of behaviors of our functions. So we've taken a limited behavior by analyzing psi at large y. We know what psi should look like at large y, and then we're attaching this arbitrary sort of h of y function so that we can start analyzing what psi looks like at small y. And we're just assuming that h of y ends up going either disappearing and becoming 1 at larger y's, or just approaching some arbitrary constant. We'll label that as just a. Okay, so now that we have a proposed guess for psi, we can try plugging this back into our original differential. So to do that, we're going to have to find the first and second derivatives of psi, so that's just product rule, so let's do that right now. D psi by dy, assuming that psi takes on this form, is going to be equal to dh by dy times e to the negative y squared over 2. And then minus, let's see, y times h times e to the negative y squared over 2. We use distributive property to sort of take out the exponential, and what we're left with is dh, oops, this is very messy, I could write this nicer, dh by dy subtracted by yh multiplied by e to the negative y squared over 2. We can do the same thing, derive it again to get d2 psi by dy squared. So this is going to equal once again using product rule. So we'll take the derivative of this term first. This becomes d2h by dy squared. And then subtracted by, and then we have to use another product rule in this term. So actually let's do this and use brackets. So we have, let's see, d by dy of y is just 1. So this is h, and then plus y dh by dy. And this is all multiplied by our exponential. And then we're adding the term dh by dy minus y times h, and then multiplied by the derivative of e this time. So this is going to give us negative y, I believe. Is that? Yes, that's just, it should just be negative. Yes, it's negative y. Sorry, I had a brain fart right there. Multiplied by our exponential, e to the negative y squared over 2. Okay, at this point, we can do a little bit, once again, of distributive property, and we're going to get, let's see, d2h by dy squared, oops, minus h minus y times dh by dy minus y times dh by dy plus y squared times h, and then this whole thing is multiplied by e to the negative y squared over 2. And from this, we can combine a few terms. This is going to give us d2h by dy squared, and then let's combine the y dh by dy's, so this becomes minus 2y dh by dy And then we have this term right here, which we can sort of distribute further and write this as y squared minus 1 multiplied by h. And then everything here is to the exponential e to the negative y squared over 2. And now let's actually plug these in to our function here, which we have, which is that, well, actually, let's copy and paste this entire thing. So we have that d2 psi by dy squared equals this. So let's plug in d2 psi by dy squared and set that equal. So what that gives us is this term is equal to y squared minus k, and then multiplied by psi, which is going to be h multiplied by e to the negative y squared over 2. So immediately we can cancel out the two exponentials. Just move everything over a little bit. And now, instead of having a equation in terms of psi, we have a function in terms of h, and our new goal is now to solve for h. So let's sort of make this a little bit neater and try to get this into a proper second differential form. So we have the same term at the front, and this is going to be equal to y squared times h minus k times h. So if we move those over to this side, then let's see, we use distributive property on this term, so we get that the y squareds cancel out, and what we're left with is this term at the front, and then plus k minus 1 multiplied by h, and this equals 0. So this is our new sort of differential function, this time in terms of h. Our goal is going to be to solve for h, and then from that point we can use h and plug it into psi to get a formula for psi, and that in turn also indirectly solves for k, and since k is dependent on energy, that also gives us the energy. So that is our new goal, is to basically solve for this, and everything else should hopefully fall into place. All right, now that we've actually obtained a differential equation for h, we can try to solve for h, but we sort of have the exact same problem as we've had before, which is that this is kind of a not so easy to solve differential equation, second order differential equation. And you know, the whole point of the analytic solution is to not have to worry about solving these like really complicated differential formulas. So we're going to once again sort of finesse out a solution for h by taking advantage of what's known as a power series. So hopefully you're familiar with what these are, but there's a theorem that's called Taylor's theorem, which states that a function, any function f of x, can be expressed as what's called a power series, where we can write it as a summation indexed by j, starting at 0 and going to infinity, of a sub j, which are coefficients, multiplied by x to the power of j. So what this is actually saying is that f of x can be decomposed into something like a naught times x plus a1 times, a naught plus a1 times x plus a2 times x squared, and so on and so on and so on. The actual requirement for this to be true is that f of x has to be complex differentiable everywhere and infinitely so. So what we mean by that is that we have to be able to take derivatives of f of x without any issues, basically infinite, as many times as we want. What this actually means graphically is that like f of x has to be smooth and it has to be continuous. And these are both reasonable assumptions to give to h, because remember that h is part of psi, and psi has to be normalizable. And in order for it to be normalizable, it has to be smooth, and it has to be sort of continuous all throughout. So this exponential is sort of smooth and continuous, so the same thing sort of has to be true for h, because if h was discontinuous, or if its derivatives had continuity issues, these issues would sort of transfer onto psi itself, and that would result in problems when we're doing things like derivatives of psi, finding things like momentum operators, things like that. So it's reasonable for us to assume that h also follows sort of this form, and we can write it as such. So there's nothing stopping us from sort of using a power series representation and just writing h to equal a summation. And I'm gonna leave out the indexes, but assume that it's j from 0 to infinity. So same indexes as this summation always, of aj multiplied by y to the power of j. And what we can do is we can take the two derivatives of this and plug them back into this differential equation in h up here. So what this will give us is dh by dy is going to be equal to the summation, once again with the same indexes, of j equals 0 to infinity, of a sub j, which is our constant coefficient, multiplied by j itself, multiplied by y to the power of j minus 1. We can do the exact same thing again to get the second derivative of h, d2h by dy squared. And this is going to give us the same summation from 0 to infinity. And you know what? Let's just write it, just to be clear. And then this summation is going to be aj multiplied by j minus 1 times y to the power of j minus 2. Now, there's nothing wrong with this method of writing it. However, it's actually mathematically going to be more convenient if we rewrite this into an equivalent form. And to see what that equivalent form is, I'm going to write out the first few terms of this. This actually, if we write it out, Griffiths gives it to us, so it saves us the trouble of having to plug everything in. But this is going to equal 2a2 plus 2 times 3 a3 times y plus 3 times 4 a4 y squared, and so on and so on and so on. So the thing that we can do here is we can note that the j equals 0 and j equals 1 terms both equal 0, partly, and that's because of this term and this term right here. So technically, since j1 and j0 are both 0, there's nothing stopping us from just starting the count at j equals 2 instead. Now, there's two ways we can do this. The first way is we can just change the index down here to start at j equals 2 instead of j equals 0. But the problem with that is that when we plug everything back into this differential equation, we're going to have two summations that are from 0 to infinity, and an additional summation that starts at 2 instead of 0. So that's not very nice. An alternate way is we can just add 2 to all of these j terms, and that'll give us the exact same sort of, that'll give us an equivalent statement. Because remember, once again, a0 and a1 are both coefficients of 0 because of the j being 0 and then the j minus 1 being 0 respectively. So there's nothing stopping us from just excluding those two terms by turning j into j plus 2 in this summation, and then keeping everything else the same. So this is actually, mathematically, for all intents and purposes, the exact same as doing a same summation from j equals 0 to infinity. But instead of using j indexes, we replace every j index with j plus 2. So this becomes a j plus 2 multiplied by j plus 1 times j plus 2, and then multiplied by y squared. So these two are identical for all intents and purposes. And once again, the reason why we're rewriting it this way is because the math, when we combine all of these, the h, dh, and d2h terms into this differential equation, the math works out nicer and we can distribute things more neatly compared to if we sort of worked with this. So let's plug everything back in. So if we do, we're going to get, let's move this over, down. And what this is going to give us is an initial summation for this. And let's close this off. And then we're subtracting by 2y multiplied by dh by dy, which is this summation term. Let's close this off. And then finally, we're adding k minus 1 times h. So plus k minus 1, and then our summation term for h, which is this. And everything ultimately equals 0. And immediately, hopefully you see, we have 3 summation terms that are all indexed the same. And we also have sort of, we have 3 summation terms that are all sort of indexed the same. So we can sort of, and also I just realized this is supposed to be y to the power of j. My apologies. This is supposed to be y to the power of j because we added j plus 2. So j plus 2 minus 2 is just j. Okay, anyway, immediately we see that we have 3 indexes, or we have 3 summations that are all under same index, so we could just combine them all into a single thing. And then the second thing we see is that we have y to the power of j, we have y to the power of the j, and then we have y to the power of j minus 1, but multiplied by an additional factor of y, so this is also y to the power of j. So we can also distribute out the y to the power of j. So if we combine everything, we get a summation, once again with the same index, j from 0 to infinity. And then we have a to the power of j plus 2 multiplied by j plus 1 multiplied by j plus 2. And that takes care of our first term. Our second term is going to be subtracted by 2 times aj multiplied by j. And then we're adding on the third term, which is going to be just aj times k minus 1. And then this whole thing is getting multiplied by the y to the j term that we sort of took out. And this whole thing is under the summation. So this is in total, this is equal to 0. And now, instead of having this really nasty sort of second order differential, we just have, we reduced it to just this, which is a lot of indexes, but it's all in terms of like j and single powers of j, and there's no derivatives. So in many ways, this is sort of a nicer form to be working with. Okay, so at this point, we have this condition of like all of these, of this formula in j and aj plus 2 equaling 0. The easiest way to satisfy this is just have this sort of term at the front just equal 0. So if this equals 0, then we have aj plus 2, j plus 1, j plus 2, subtracted by 2aj times j plus aj k minus 1, and this equals 0. And that's the simplest condition for sort of this to be true. So if we assume that this is the right condition, then what hopefully you see that we can sort of define a recursive relation here, because we have subsequent sort of indexes defined in terms of prior indexes. So what we can do is we can isolate aj plus 2 on one side and move everything else to the other side. So what we get is aj plus 2 is equal to 2aj j minus aj k minus 1. And then all this is divided by j plus 1, j plus 2. And automatically we can distribute out the aj, so what we have left is 2j plus 1 minus k over j plus 1, j plus 2 multiplied by aj. And just like that, we have a recursive formula for sort of the subsequent coefficients of h. So this formula does have a bit of subtlety to it. And the biggest one is the fact that the indexes are defined in terms of j plus 2, not j plus 1. So we don't find successive terms, we find successive we find the success of every other term. So what this sort of implies is that there's actually 2 different recursion formula sets. One of them starts at j equals 0 and gives us 2, 4, 6, 8, all the even terms. The other one starts at j equals 1 and gives us 3, 5, etc., and all the odd terms. So what this does is that if h is equivalent to like this summation of aj times y to the power of j, starting from j equals 0 to infinity, what will happen is that this is actually going to end up being split into sort of an odd series of terms plus an even series of terms, where sort of the odd series is defined as a1 times y plus a3 times y cubed plus etc, etc, etc. And then we have the even series defined as a naught plus a2 y squared plus etc, etc, etc. So what happens now is that we have to sort of determine both a1 and a0 to sort of define h completely. Now, this next part is, in my opinion, probably the most complex part of this chapter, or not this chapter, but this section, and not because of sort of mathematical rigor, but more so because there's a very subtle problem that comes from using this type of recursion formula, and it's not necessarily something that's easy to sort of catch when you're sort of doing this on your own. And to actually find out what this problem is, what we have to do is we have to take this recursion formula, we have to look at it in the case where j is very large. So if we take the positive, the positive infinity limit for j, what will happen is that the 2j at the top dominates and the j squared at the bottom dominates. So what you have left is 2 over j times aj. So let's write this out. Whoops, that's not what I wanted to write. A of j plus 2 starts behaving sort of like 2 over j times a j when j is large. Now, this doesn't seem like it's going to be a problem. However, it actually will sort of be. And to see what that actual problem is, we're going to start sort of doing a little bit of mathematical tomfoolery, I'd like to put it as. So note that this is an equation that is a recursive in terms of its indices. So what we can do here is that we can define a new recursive relation by sort of redefining this index j and changing all of the j terms into that new definition. So suppose that I say that I want to change my j's to 2j's. In that case, what will happen is that this new recursive relation will become a of 2j plus 2, behaving roughly like 1 over j, multiplied by a of 2j. So this is still a valid recursive relation. It is effectively the same as the one above. The only difference here is that because our indexes have been sort of changed, this equation will either give less terms than this upper one, or it'll give extra terms that we don't necessarily want. So what will happen is that we can do whatever math we want with this, and the ending result will be valid as long as we sort of revert back to the original j afterwards. So basically, whenever we do sort of these changings of indexes, we have to keep track of them and sort of reverse them later on. So I'm going to keep track, and I'm going to say this is the first thing I did, and I'm going to keep going. So we're going to do another change in index, and we're going to say, okay, from this point, we're going to change j to j naught plus k. And this is going to be our second index change. So if we do that, what we're going to get is a of 2j plus 2k plus 2 is equal, or not necessarily equal, but behaves something like 1 over j plus j, or j naught, sorry, not j, but j naught, plus k multiplied by a times 2j naught plus 2k. And by j naught, I feel like I should make this clear. J naught is a constant. It's some arbitrary constant we don't care about, and k is actually the new index here. So what we're doing is we're switching from an index of j to an index of k with this extra sort of random term at the front that the reason of which I'm adding it will become clear sort of later down the line. So what we have here is, note this term, which is of interest, because what we can do is we can define j equals j naught plus k minus 1 and plug this back into this above equation to get another recursive formula. So if we do that, a of 2j plus 2 is going to become a of 2j naught plus 2k minus 2, and that cancels out with the plus 2, and this behaves something like 1 over j naught plus k minus 1, multiplied by a of 2j, which is 2j naught plus 2k minus 2. And from here, this can sort of be iterated upon again, defining j equals j naught plus k minus 2, and so on and so on and so on. And we can keep on doing this forever. Suppose that we did this to the point where sort of this term grows until it equals k exactly. So it'll cancel out with k, and then we're left with j equals j naught. If we do that, then what we're left with is a of 2j naught plus 2k plus 2 is going to equal, we have j naught plus k from the first iteration, we have j naught plus k minus 1 from the second iteration, so on, so on, so on, so on, multiplied all the way down to j naught. And then this is the bottom of our fraction, so we add a 1 over at the top, and then we have a of, and then we have 2j naught plus 2k minus 2 minus 4 minus 6, etc., until that cancels out with the 2k. So this is just remaining is 2j naught. Now, just from looking at this, hopefully you see that it's sort of just begging to get a sort of factorial conversion. So we can convert this bottom term to j naught plus k factorial, and to account for all of the extra terms after j naught, so like j naught's minus 1, j naught minus 2, and all that stuff, we can multiply the top by a factorial of j naught minus 1, and that cancels out all those extra terms. And then we have a of 2j naught. And let's write the start like this as well. Now, what we realize here is that, first off, this term over here is just a constant. And the same is true for this, because remember, j naught was defined as an arbitrary constant. So j naught minus 1 is also a constant, and a sub 2j naught is going to be whatever that coefficient term is. So there's nothing stopping us from absorbing everything on the top into just a single constant that we're going to call c, and we divide it by j naught plus k factorial. And from this point, we can switch back to our original sort of indexes. So remember, we did two sort of switches. So let's start with this one, j equals j naught plus k. If we do that, then this is going to give, so if j equals j naught plus k, then what we're going to get is a, and then 2j naught plus 2k, which is just 2j plus 2, is equal to c over j factorial. The next thing we did, or the first sort of index change we did, was switching from j to 2j. So if we want to reverse that, we're going to change j to 1/2 j here. And if we do that, what we're going to get left is a, 2 times 1/2 is 1, and then j. So j plus 2 is equal to c over j half factorial. Now, at this point, what we have here is sort of something that can get plugged back into h, because recall that sort of h is a power series. So h is defined as a summation from j equals 0 to infinity of a sub j multiplied by y to the power of j. Now, there's nothing sort of, there's nothing really stopping us from sort of plugging this in, because what happens here is that remember that psi is equal to h times e to the negative y squared over 2. And this approximation here was done under the assumption that y is large. And if y is large, then what will happen if we're doing like a power series is that, you know, the higher orders of y are going to sort of dominate over this equation, because y to the power of like 10,000, when y is a super big number, is obviously going to be like super large compared to like y to the power of 10, which is going to be negligible in comparison. So this power series is going to have all of the higher powers dominate as a result of the fact that y is large, and we just analyzed what the coefficients sort of become when sort of the j terms are very large. So there's nothing stopping us from just converting to this and making that direct substitution. So let's do that. Let's switch to j from j to j plus 2. So this becomes j equals negative 2 to infinity of a j plus 2, y to the power of j plus 2. And then from here, we have this. So this is going to be equal to the constant c times our summation from j equals negative 2 to infinity of 1 over j half factorial times y to the power of j plus 2. And then from here, we're going to do yet another sort of index change, and we're going to switch back to j equals 2j. So if we do that, then h is going to equal c times a summation. Now the indices are going to be a little bit messed up, but it's actually not that important what this bottom term equals. It's going to equal like something. So I'm just going to mark it as a question mark. And the top is still infinity. And what we're going to get is 1 over j factorial multiplied by y to the power of 2j plus 2. Now, this is where sort of the whole idea of analytical methods come into play, and that we're not solving this exactly, but instead we're sort of taking advantage of some of the behaviors of this math. And what I mean by that is that the formula for an exponential function can be represented as a power series. So e to the power of like y can be expressed as sort of a summation from j equals 0 to infinity of 1 over j factorial times, y to the power of j. So if we have, e to the power of 2y, for example, this is going to give us, a summation of j equals 0 to infinity of 1 over j factorial again, and then y to the power of 2j. Or, sorry, my apologies. I just realized I messed this up. It's e to the power of y squared. E to the power of y squared is going to give us something like y squared j, which is just y 2j. Or not 2y, 2j. So if we look at this, this looks very similar to this. We have sort of this 1 over j factorial term that's shared, and then we have a y to the 2j. The only difference here is that y is to 2j plus 2 instead. And the other difference is that we start at some positive sort of index or negative index, whatever it is, instead of j equals 0. But other than that, it's sort of reasonable to just say that h goes roughly kind of like e to the y squared. Because it's sort of close enough, all of the things that sort of differ from it don't really matter that much. Substituting 2j with 2j plus 2 will only make it grow faster compared to e to the y squared. And the indexes sort of don't really change that much either. So the reason why this is important is because psi is defined as h times e to the negative y squared over 2. So if e to the y squared, if h behaves something like e to the y squared, then psi is going to behave something like e to the y squared over 2. Because, we have e to the y squared times e to the negative y squared over 2. And this is a problem because this is obviously not normalizable. If we graph this, it looks something like this, and it just goes to infinity, which is not physically realizable. So this is a problem because by doing this, we've sort of resulted in a wave function that's not physically realizable. Okay, so the question now is, what do we do to sort of resolve this problem of psi being non-normalizable? And the answer turns out to be something called truncation. So what we mean by that is that we know that h is defined as a power series over y. So this is equal to aj times y to the power of j. And we also know that sort of y is large. And the fact that y is large means that sort of the later powers of y to the j will sort of dominate this power series compared to the earlier powers. And that is what's causing sort of this e to the y squared behavior for h. So to prevent h from behaving like this, what we can do is we can impose a condition so that after some point in j, the successive aj coefficients all go to 0, and that's called truncation. So we know sort of that a of j plus 2 follows this recursion formula of 2j plus 1 minus k over j plus 1, j plus 2, aj. So what we can do here is we can say, okay, there's some sort of critical value for j, and we'll call it j equals n. So at j equals n, a of n plus 2 is going to equal 0. And what that does is that all successive terms in this series will also equal 0. Because if a of n plus 2 equals 0, then a of n plus 4 is equal to whatever constants this becomes times a n plus 2. But if this is 0, then a n plus 4 is 0, and so is a n plus 6, etc., 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 etc. So if we sort of do this, then what will happen is that all of the higher power terms after a certain point sort of terminate, and what we're left with is just a sum of a bunch of lower power terms. And instead of behaving like e to the y squared, h is going to behave like whatever behavior dominates these lower power terms. The only problem that comes about from this is that a is defined in terms of j plus 2, not j plus 1. So what happens here is that this this is a recursion formula that splits into two different formulas. If we have A1, then we have an odd series. If we start with A0, then we have an even series. So this restriction only applies to one of those two series. And what I mean by that is, let's say, for example, that n terminates really early. So let's say that A3 is going to equal, what is that? N is going to be 1 in that case. So 3 minus k over 2 times 3 multiplied by A1. And A2 is going to equal, in this case, n is 0, or j is 0. So this is going to be 1 minus k times 1 times 2 times A0. K is the only thing that's a variable in both of these equations, and k is going to be predetermined by the energy, and the energy is what we're trying to solve for. So the energy is going to be whatever. So let's suppose that n equals 3. Let's suppose that our truncation term is n equals 3. What will happen is that if a3 equals 0, then that implies that k has to equal 3, because a1 is a non-zero term. These are both non-zero terms. So k has to equal 3 so that this top term equals 0, so that a3 equals 0. And then we have a5 equals 0 and a7 equals 0, and all the odd terms go to 0, and that's all fine and dandy. The problem is that a2 does not necessarily go to 0 now, because k is predetermined by the fact that a3 goes to 0 to equal 3, and if we plug in 3 here, this doesn't give us 0, because a0 isn't necessarily 0 either. So what will happen is that all the odd terms get truncated, but the even terms still continue on to infinity, and we have the same problem, where like h is going to be dominated by these super high-powered even terms, and we're going to have the same problem of going to something like e to the y squared. So to take care of this, to resolve this, what we have to do is we have to say that, okay, n determines like sort of which one of these two series actually means anything. So if n is odd, then what that means is that the odd series truncates. And if n is even, then the even series truncates. So what the problem here is then that, then the odd series truncates. I forgot to write that. Okay, so if the odd series truncates, then we're left with this even series that doesn't necessarily go to 0. In fact, it's more likely to blow up than anything. So the requirement for sort of h to not behave in this e to the y squared way is that the even series has to just completely equal 0. A0 has to equal 0, so that a2 equals 0, so that a4 equals 0, and so on and so on. If n, which is n, remember, is sort of the terminating number after which all of the successive terms are 0. If n is an even number, then the even series gets truncated perfectly fine, but the odd series gets left alone. So a1 has to equal 0, so that a3 equals 0, so that a5 equals 0. So in reality, h is going to equal either h odd or h even. It's never going to be their sum, because one of these two is always going to be 0. So if h equals h odd plus h even, always one of these two is going to equal 0, and we only have to ever deal with one. So because of that, we say that h is actually equal to h odd or h even, and that solves sort of this problem of h behaving very badly when we go to like higher values of j. Okay, now that we've sort of taken care of all of the problems that arose because of this recursion formula, we can actually start using it to obtain k. So we have our condition that a of n plus 2 has to equal 0. So this implies that if we replace j with n, then 2n plus 1 minus k divided by n plus 1, n plus 2 times an has to equal 0. An doesn't necessarily equal 0, and we also have that n plus 1 and n plus 2 don't necessarily equal 0, so our requirement is then for this numerator to equal 0. So that means 2n plus 1 minus k equals 0, otherwise meaning that k equals 2n plus 1. Now, we defined k at the very start of this section in terms of energy, so we know that k equals 2e over h bar omega. So by that logic, E is going to equal 1/2 h bar omega times 2n plus 1 therefore, this equals h bar omega over n plus 1/2. And just like that, we've sort of recovered the energy formula for the simple harmonic oscillator that we solved back in the analytic method. And what this implies is that, so in order to satisfy this a n plus 2 equals 0 truncation statement, we have to pick specific energy values so that this is true. And the specific energy values we pick correspond with these n terms, and this is what determines the energy. This is what determines sort of whether we're in the ground state or the first excited state or the second excited state, etc., etc. So what this means is that sort of the excitation state, the end state of a given psi, because remember psi is determined by these states, end states, psi 0, psi 1, psi 2. This determines basically how many terms we go up to. So whether or not this is, psi 0 is just going to equal like a0. Psi 1 is going to be like, a1 times y, and then psi 2 is going to be like a0 plus something times a2 times y squared, and so on and so on. So basically, the higher energy values we go, the more sort of successful terms in the power series for h that we have to include. The next thing we can do is we can actually start writing out sort of the general wave functions. So suppose, for example, that we wanted psi 0. So in this case, n equals 0, so we're going to be dealing with sort of the even truncated series, and the odd ones just go to 0. We have sort of our definition from earlier. So if n equals 0, then in this case, we have sort of whatever a0 is going to be, and then we have a2 is going to terminate. So in that case, a2 just equals 0, so we just have a0 equals like whatever a0 is, and our psi term, which equals h times e to the negative y squared over 2, is going to just equal a0 times e to the negative y squared over 2. Now, this looks pretty similar to the actual psi 0 wave state, because we know from sort of the earlier sections that psi 0 of x is going to equal m omega over pi h bar to the power of 1/4 times e to the negative m omega over 2 h bar to the power of x squared. So this is just what y squared over 2 simplifies to if we actually define y in terms of x from earlier, and this is what a naught is. So it seems like sort of our guesses have been pretty good, and this actually is the correct way to define psi in the analytic method. We can do the same thing for n equals 1. So if we want psi 1, for example, n equals 1, that means we're dealing with the odd terms only. So that means a3 automatically equals 0, and so do any subsequent odd terms, and we have a1 equaling whatever the heck it is. So h is going to then equal a1 times y, so therefore psi, which equals h times e to the negative y squared over 2, is going to equal a1 times y times e to the negative y squared over 2. Once again, we can do the same thing with psi 2. So psi 2 is going to give us n equals 2. So we have, a naught equals whatever it is. A naught equals whatever it is. A2 is going to equal, according to this formula, which let's just copy paste it down again. A2 is going to equal, since j equals 0 here, we're going to have, let's see, 0 plus 1 minus k over 1 times 2 times a 0. So this is just going to be 1 minus k over 2, a 0. So ultimately, h2 is going to be a naught plus 1 over, well, actually, a2 y squared. So this is going to equal a naught plus 1 minus k over 2 a naught y squared. Or we can distribute out the a naught, and this is going to give us 1 plus 1 minus k over 2 y squared. And at this point, remember, we can solve for k under the requirement that sort of a
a4 has to equal 0. So if a4 equals 0, then this equals, let's see, 2 times 2 is 4, 5 minus k divided by 2 plus 1 is 3, and then 2 plus 2 is 4 times a2. So k has to equal 5. So that means 1 minus k is negative 4. So this equals a naught 1 minus 2y squared. So therefore psi is going to equal h of 2 multiplied by sort of the exponential. So this is a naught 1 minus 2y squared times e to the negative y squared over 2. Now, hopefully you see a pattern here in that sort of these h terms are all going to be sort of successive polynomials of either odd or even degrees, and the actual pattern for this is actually something that's very popular in math. This specific type of polynomial is called a Hermite polynomial, and they are defined sort of like this. If you go on like the Wikipedia, you could find it down to like h100 or something, I believe, and it just goes on. The Hermite polynomials themselves aren't too important, but what is important is the fact that this actually gives us sort of a method to actually write out a general solution for psi n using the analytic method, whereas sort of before, when we were using the algebraic method, we were kind of forced to just apply raising and lowering operators just multiple times in order to get like the more extreme sort of higher states. So more generally, the actual normalization method for the Hermite polynomials is a little bit more complicated, and it's not really something that's going to be covered because that's probably better left to like a math course or something. Griffiths just gives us the answer, so we're just going to write it out here. It turns out that the arbitrary, sort of the general solution for psi n of x for a harmonic oscillator is going to equal the m omega over pi h bar term that appears always, as we've seen so many times, and then multiplied by this extra factor of square root of 2 to the power of n times n factorial, where n is, you know, the nth state of the oscillator, and then multiplied by the Hermite polynomials, which are labeled hn of y. In this case, y is what we're calling this sort of variable. This variable is technically psi, but it's really hard to draw, so I've just been using y this whole time, and then multiplied by e to the negative y squared over 2. So everything here is what we would expect. The only difference is this term of 1 over square root of 2 to the power of n times n factorial, and that comes from sort of having to normalize the Hermite polynomials. And once again, since that's more of a math exercise, it's not going to be covered extensively here. So there's a final point that Griffiths sort of makes sort of in the middle of this chapter that I feel like would be better sort of reserved for the end. And it's this little digression talking about sort of the fact that harmonic oscillators only allow for specific values of E. So we know that for harmonic oscillator, the values of E have to be defined such that they equal h bar omega times n plus 1/2. Now, the thing is, if you actually plotted this function on a graphing program, what you'll find is that there actually are valid solutions for psi for every single possible value of E. There's actually infinite solutions, which is what we would expect from a classical system. E can be anything. It's a continuous variable, and every single sort of value of E is valid as a valid solution of psi. The only problem is that not all of them are necessarily normalizable, and the ones that aren't normalizable are the ones that aren't physically realizable. So therefore, we're sort of restricted. And it turns out that these terms are exactly the ones that actually do give rise to sort of physically normalizable solutions. So if we graph them, what'll happen is, for example, E naught, the base ground state wave function, is equal to 1/2 h bar omega. Now, this is, you know, if we write it as a decimal, this is 0.5 h bar omega. Now, if we sort of, if we graphed psi at, for example, 0.49 omega, so at E equals 0.49 omega, or h bar omega, if we graphed sort of, you know, y with respect to psi, what the graph looks like is something like this. So obviously, you know, this goes to infinity over here, and it also goes to infinity to the left as well. So that's not normalizable. So this is not physically a realizable function. However, alternatively, if you sort of try at E equals 0.51 h bar omega. So we're trying directly to the left and to the right of 1/2 h bar omega. The resulting graph for this one looks something like this. So if, whoops, that's a bit messy. We can probably draw this a little bit better. There we go. So at y and psi, the graph ends up looking something like this. So this is sort of the same problem because, you know, the probability density is based on magnitude of psi squared. So what's going to happen is that this just gets flipped up, but it's still going to infinity at the left and right ends. It's just, it gets flipped. And this doesn't really have any significance to the actual chapter. It was just an interesting thing that I felt was worth mentioning because it sort of graphically visualizes why sort of the valid sort of values of energy are what they are. Because apparently sort of these points are the 1/2, you know, points dictated by 1/2 h bar omega, or just more generally points dictated by this formula, are the ones at which sort of this graph oscillates between like the positive exploding to infinity at positive values versus exploding to like negative infinity at negative values.